In this video, we're going to continue our study of Newton's laws of motion. We're going to look at some problems involving both inclines and friction. When we're solving problems using Newton's laws, we always want to follow these same steps. Step number one is always to draw a free body diagram for each of the objects involved in the problem. Then sometimes it helps to choose an x and y axis that's different from normal to simplify the calculation. Where that's going to be true is on any problem involving an incline. If we have multiple objects moving together, then we have to define which direction we mean by positive in terms of their motion. We're going to always have to resolve our forces into their x and y components, and then finally we can apply Newton's second law for each object in each direction. Let's look at the following problem. What is the acceleration and what is the normal force for this block on the incline? And here we're going to do the problem first with no friction. Our first step then is to draw the free body diagram. In this case, there is the normal force. Remember, normal means perpendicular, so perpendicular to the surface, and then the force of gravity, mg. We can see that those two forces can't cancel out because they're not in opposite directions, and therefore this mass is definitely going to move. The next thing we want to do in this problem is figure out what this angle is. And the reason we want to figure that out is the following. First of all, on an incline, we're going to set up our axes so that the x-axis is along the incline and the y-axis is perpendicular to the incline. The reason we do that is that way we'll only have acceleration in the x direction and there'll be no acceleration in the y direction. It dramatically helps us to solve the problem, makes it much easier. Generally, in a problem involving an incline, we're given this angle, theta, the angle of the incline. Let's see how that relates to our free body diagram. I'm going to draw a line straight down here, so one that's perpendicular with the bottom of my ramp. And you'll notice then if this angle is theta and this angle is 90, this angle is 90 minus theta, simply because they're 180 degrees in a triangle. I'm now going to draw an additional line. This line is perpendicular to the surface. And so you'll notice that if this is 90 minus theta, this angle has to be theta. And what I've just done then is I've shown you that this angle is also theta. So the angle of the incline is the same as this angle, and we're going to need that in the problem. Let's go ahead then and figure out the components of mg. The reason that we're breaking mg into its components is because, remember, we want the components either in the x or the y direction. And since we've rotated our axes, you'll notice the normal force is in the y direction, but mg is both in the x and the y direction. So let's figure out what this component and what this component are. Notice that mg is the hypotenuse. This is the right angle. So, what is this side equal to? Well, it's common for people to say sine, but the correct answer is mg cosine theta. And this side here is mg sine theta. This is important. Make sure that you understand this. Now, why is it that? Well, because you'll notice that this side is the opposite side from theta, and this side is the adjacent side to theta. If I redrew the triangle this way, where here's theta, here's mg, then it'd be more obvious that that's mg sine theta, and this down here is mg cosine theta. Okay, so just because of the way the triangle is oriented, it's easy to get confused by that. Once we've got that figured out, we can now apply Newton's second law in each direction. In the x direction, the net force is equal to the mass times the acceleration. And this is what we're trying to find, because again, the x direction is along the incline. If we look at our free body diagram, the only forces that are acting in the x direction, in other words, along the incline, is the component of mg sine theta. So that's got to be equal to max. And you'll notice we can cancel out the m's, and we find that the acceleration is g sine theta. Let's stop and think about that for a minute and make sure it makes sense. Notice that if theta is 0, in other words, the block is on a flat surface, the sine of 0 is 0, so we would get an acceleration of 0. Also, so let me just write that. If theta is 0, ax is 0, so that makes sense. Notice if theta equals 90 degrees, then ax is equal to g. Now the reason it's not negative g is simply because we've defined down the incline as positive. So if the incline is completely vertical, then the object is just going to accelerate with a value of g. So that makes sense. Let's look at the y direction. F net y equals may. Now, in the y direction, there is no acceleration. Remember, that's why we rotated the axes, so that the acceleration would only be in the x direction. So the right-hand side there is 0. Let's look at what forces are acting in the y direction. We've got the normal force acting in the y direction. And then we have just a piece of mg in the y direction. And again, we can see that's mg cosine theta. That's down in the y direction, so I'll write negative mg cosine theta. And again, because the acceleration is 0 in the y direction, it's got to equal 0. And therefore, what we find is the normal force is mg cosine theta. It's always a good idea, again, to look at some situations that we already understand to make sure that this makes sense. Notice that if theta is 0, then cosine of 0 is 1, the normal force just would be equal to mg. Well, that makes sense for an object on a flat surface. If theta is 90 degrees, notice the cosine of 90 is 0, and the normal force would be 0. Therefore, if our ramp is completely vertical, there really is no force that it's exerting on the object. Effectively, the object would just be falling next to it. This is an important slide because really anything we do with ramps involves at least this information. Let's take a look at a more complicated example. Again, we'll do this one without friction, and then we'll add friction in a later problem. The question is, what is the acceleration? Notice this is a more complicated problem because we now have two objects connected together by a string. However, our process of doing these problems is always the same. Step 1, draw the free body diagram. So let's draw the free body diagram for object number 1 and object number 2. Object number 1, very straightforward. We've got the tension in the string acting up on the object. Remember, we use F subscript T for tension. And we have the weight of the object, m1g, acting down. Now, for object number 2, it's going to look fairly similar to the last problem that we looked at. We've got the normal force that is perpendicular or normal to the surface. We've got the force of gravity, m2g, which is straight down. But now we also have a force this way, which is the tension. Notice that that's a right angle because the tension is directly up the incline and the normal force is directly perpendicular to the incline. We also know from our previous work that if this angle is theta, then that means this angle is also theta. Remember again, that's the right angle, and mg, or m2g in this case, is the hypotenuse. So this component of mg is again the adjacent component, m2g cosine theta. And this component is the opposite side, so it's m2g sine theta. So we've got our free body diagrams, and we've broken into components any force that's not either in the x or the y direction. Now, for object number 1, if we define up as the positive direction of motion, then for object number 2, that would correspond to down the incline being the positive direction. The reason this is important is these two objects are going to be moving together. So we're just going to have one acceleration for both object 1 and object 2 because they have to move together. And therefore we want to make sure that if object 1 is moving up and we call that a positive direction, well, that corresponds to when object 2 is going down the incline. So we have to specify that as the positive direction for object 2. Now in this problem, let's look at the direction of motion. And so when we have objects moving together, we're looking at the direction of motion for both objects. So for object number 1, it's moving in the y direction. So let's write down F net y 1, so the net force in the y direction on object 1 is equal to m1a. I'm not putting any subscripts on the a's because a is the same for both objects. For object number 2, its direction of motion is what we would call the x direction for it. In other words, along the incline. So I'll write F net x2 is equal to m2a. And now we want to go ahead and fill in the forces. On object 1, the net force would just be Ft minus m1g, and that's got to equal m1a. For object number 2, down the incline, we have this force, m2g sine theta, but then along the incline up in the upward direction, we have Ft. Therefore, we would have m2g sine theta minus Ft, and that equals m2a. Once we have these two equations, you'll notice that we have that situation of two equations and two unknowns. We don't know what the tension is. We don't know what the acceleration is. In this case, we're just asked to find the acceleration. And therefore, what we want to do is take those equations, and as we've learned in previous videos, the best thing to do here is to add the equations. So we have Ft minus m1g equals m1a, and we have m2g sine theta minus Ft equals m2a. You'll notice that when we add these, we see that the Ft's cancel out. And again, that's why we do this. It's our check. Any of those internal forces, or what are effectively action-reaction pairs, should cancel out when we look at the two objects together as one object. And so what we get is m2g sine theta minus m1g is equal to m1a plus m2a. Let me just recopy that on the next slide. We have m2g sine theta minus m1g is equal to, and I'm going to just factor out the a here, m1 plus m2 times a. And therefore, our solution for the acceleration, remember we always want to solve algebraically completely, is m2g sine theta minus m1g over m1 plus m2. Okay, before we plug in the actual values in the problem, let's just make sure that our answer makes sense by looking at some kind of extreme solutions. If m1 is 0, in other words, if we get rid of that, what does our answer simplify to? Well, you'll notice that the m1 term goes away, and the m1 goes away in the bottom, and what we get is that the acceleration of block 2 would just be g sine theta. Well, that makes sense. That's the result we had from the simpler problem when we just had a block on an incline. Now, if instead of saying what happens if m1 is 0, what happens if m2 is 0? Well, now we lose that m2 and we lose that term. And you'll notice we get minus m1g over m1, or a is equal to negative g. Notice that that makes sense, because if m2 isn't there, m1 would just accelerate at negative g, because down is negative for that object. It would just fall with the acceleration due to gravity. So again, it's always good to go through and check your solution by putting in things that you can figure out conceptually and see if they make sense or not. To finish off the problem, we now plug in our values. m2 is 2 times 9.8 for g times the sine of 30 degrees minus m1, which is 1, times 9.8 divided by 1 plus 2. Now, if you calculate that, what you'll notice is it happens to come out to 0. When I made up this problem, I just made up kind of random numbers when I did it. But what I realized is that, of course, the sine of 30 degrees is a half. And so because I made m2 twice as big as m1, and I put it on an incline of 30 degrees, I happen to pick the situation where they balance each other. Obviously, if we increased m2, we would then get a positive acceleration because they would be going down, or m2 would be going down the incline. If instead I made m1 more massive, then we would end up with a negative acceleration, meaning that m2 would be going up the incline and m1 would be going down. Let's take a look at this problem. A block is given an initial velocity up an incline of negative 30 meters per second and a coefficient of friction of 0.3. How far up the incline will the block travel? So you know what our first step is. It's to draw the free body diagram. What I'd like you to do is pause the video and draw the free body diagram. Okay, so let's see how you did. The reason I wanted you to try to draw this first on your own is there's a very common mistake that students make in this problem, and I wanted to point that out to you. The question here is, how many forces are acting on our block? Is it 3 or is it 4? The common mistake is to say that there are 4 forces acting on the block, but in fact there are only 3. We definitely have the normal force, again perpendicular to the incline. We've got the force of gravity acting down, and we've got the force of friction. In this case, it's kinetic friction because the object is moving. Notice that this is a right angle because friction is always directly opposite the direction of motion, and the normal force is perpendicular. What many students like to do is they want to put a force in the direction of motion, but there is not a force in that direction. Just because the object has a velocity doesn't mean there's a force. Okay, so in the initial situation of this problem, we simply know the object is moving up the incline, but there is no force pushing it up the incline. It just has an initial velocity. So be really careful of that. It's very easy to want to put a force whenever we have a velocity, but just because there's a velocity does not mean there's a force in that direction. All right, so that's our free body diagram. It's just those forces. We know our next step would be to break mg into its components. And again, important to remember that this is the right angle in the triangle, and this is theta, which is the same as the angle of the incline. So once again, this would be mg cosine theta, the adjacent side, and this would be mg sine theta, the opposite side. Once we've got that figured out, we can now go ahead and figure out the problem. Remember that when we have friction in a problem, it always makes sense to first find the normal force, because we need that to be able to figure out the force of friction. Since in our problem here we are setting x and y, and actually I'm going to set my origin to be at the bottom of the incline. So in other words, here's my y component and here's my x component. Let's start with the y direction then. The net force in the y direction is equal to MAY. Again, always starting with Newton's second law for each component. Now, in the y direction, again, which is the direction perpendicular to the incline, we have the normal force, and then we have that component of gravity. So minus mg cosine theta. And we know that the acceleration in the y direction is 0, because again, that's why we rotate the axes, because there's no acceleration perpendicular to the incline. Therefore, we learn that the normal force, once again, is mg cosine theta. And you're going to find that's always what it is on an incline, but I always want to see you work it out and show me that. Now we also remember that the force of kinetic friction is the coefficient of kinetic friction times the normal force, and therefore the force of kinetic friction in this problem is mu k times the normal force, which is mg cosine theta. So we've now not only found the normal force, but we figured out now what the force of friction is in this problem. Now we're trying to find the acceleration, so let's go ahead and write down Newton's second law in the x direction. F net x equals max, and ax is what we're trying to find. I've got to look at my free body diagram carefully here. Notice that both Fk, the force of friction, and this component of gravity are both in the direction along the incline, and that therefore they're both positive. They're both in the positive direction. So I get Fk plus mg sine theta equals max. Now if you think about that, that makes sense because the object is moving in the negative direction. Both friction and gravity are trying to slow that object down. So if it's moving up the incline and slowing down, that means the acceleration ultimately should be positive. Therefore, I can now solve for the acceleration. Ax is just Fk plus mg sine theta divided by m. And I'm going to now substitute in what we figured out here. Ax equals mu k mg cosine theta plus mg sine theta divided by m. You'll notice that I didn't give m in the problem, and that's not an issue for us because we can see that both of the terms in the numerator have an m in them, and so we can cancel that with the m in the denominator. Now I can go ahead and find my value for the acceleration. We've got mu k times g cosine theta plus g sine theta. Or the acceleration is equal to the coefficient, which is 0.3, times 9.8, times the cosine of 30, plus 9.8 times the sine of 30. When you calculate that, you should find the acceleration is 7.45 meters per second squared. Again, it makes sense to have a positive acceleration because we've got a negative velocity and the object is slowing down. So we know the velocity and the acceleration have to be in opposite directions. Okay, now that we've got the acceleration, we can solve for the question we're being asked, which is how far up the incline will the block travel? At this point, once we know the acceleration, it's just a kinematics problem. Remember that I set my origin here, and therefore you'll notice that the block should end up with a negative final position because we're to the left of the origin. Looking at the kinematic equations, we want a kinematic equation that doesn't involve time. In other words, we know the final velocity is 0, but we don't know how long it takes to get up the incline. And of course we could figure it out, but it's not something that we know. Again, we're saying that the initial position is 0 because we've set our origin to be where the block starts, and therefore what we're looking for is x. What is that final position? The best equation then to use that doesn't involve time would be v squared is equal to v naught squared plus 2a x minus x naught. We can see that our initial position is 0, our final velocity is 0, and therefore we get that 2ax is equal to negative v naught squared. And therefore x is equal to negative v naught squared over 2a. Notice that that negative sign makes sense because we know the object is ending up to the left of the origin. Plugging in the values, we have negative. Now v naught itself is negative, but of course that negative sign goes away because we're squaring v naught. And then we divide by 2 times our acceleration that we determined to be 7.45. What we end up with is negative 60.4 meters. And again, that makes sense because the object ends up to the left of where it started. Let's look at one last problem. A driver locks his brakes and the car skids to a stop. The coefficient of kinetic friction is 0.7 and the car's initial speed was 30 meters per second. What is the stopping distance? The first thing we want to notice in this problem is that this car doesn't have anti-lock brakes. So no anti-lock brakes. We know that because the car skids. Okay, so unfortunately no anti-lock brakes. The car is going to skid to a stop, and we want to understand what the stopping distance is. So let's think about what we know and what we don't know. This is again a problem that we're going to have to use both Newton's second law, or Newton's laws of motion, and we're going to have to use kinematics. So let's draw out the kinematics picture first. Here's the road. We've got our car. And our car has an initial velocity of 30 meters per second. We can say that it starts at x naught equal to 0. So we'll set our origin at the starting point for the car. Our car is now going to skid to a stop. So our final position of the car is what we're trying to find. Right? We're trying to find where does it end up? What was the stopping distance? You'll notice that we don't know how much time it takes for this stop to occur, but we do know the final velocity is going to be 0. Well, in order to solve this problem, we can see that what we're going to have to find is the acceleration. And therefore, we can use Newton's second law to figure that out. Let's draw the free body diagram for the car while it's stopping. So while the car is stopping, there are only 3 forces acting on the car: the normal force, the force of gravity, and the force of kinetic friction. In other words, the sliding of the tires on the road is exerting a force on the car of Fk. And those are the only forces acting. If we look at the y direction, we can figure out what the normal force is. Notice this is that very simple situation. We have no acceleration in the y direction. We only have two forces, Fn and mg, and therefore the normal force is just mg. Once we know that, since the force of kinetic friction is mu k times the normal force, we can write that the force of kinetic friction is mu k times mg. You'll notice that I didn't give you the mass of the car, so we've got to hope that the mass is going to cancel out. Now let's look at the x direction, and we're going to be plugging in that Fk in the x direction. The net force in the x direction is the mass times the acceleration. And again, that's what we're trying to find. We need to know the acceleration, and then we should be able to do kinematics to find x. The only force acting is Fk, and it's acting to the left, so I'm going to put in negative mu k mg, and then max on the right. Notice here that the m's do cancel out, so I end up with the fact that the acceleration is negative mu k times g. If you take 0.7 and multiply by 9.8, what you're going to find is that the acceleration is negative 6.9 meters per second squared. Notice that that makes sense. The object is moving to the right and slowing down. Therefore, the acceleration has to be negative. Once we've got that, we can now go ahead and do kinematics. V squared is equal to V naught squared plus 2a x minus x naught. Our initial position was 0. Our final velocity is 0. And therefore, we get x is equal to negative v naught squared over 2a. Notice that we want to be careful and make sure the negative signs work out correctly. We've got negative, then we've got 30 squared. We're dividing by 2 times the acceleration, which is negative 6.9. And you'll notice that those negative signs are going to cancel out. We know that they should because we know that x is going to be positive because the car is ending up to the right of where it started. And so we get 66 meters for our answer.